questions?
Good morning.
Good morning. All right, good morning, everyone. So we took a quiz last, what day is it? Thursday, right? So I'm going to pass those back, okay? Any objections to me just passing these around? Y'all comfortable with that?
Passing it back to us? Or passing it back to
I'm going to start it and let it just go around. Sometimes people are like, oh, I don't want anyone to see my grade. Everyone's okay? No one's going to have any issues? Sure. All right, there we go. Just grab yours out, pass it around, please. When I was in high school, I went to a private school, and when they passed out the grades, they always started with the lowest grade first, and then they went in sequential order to the highest student. Yeah, so I mean, there was like, you couldn't hide. You couldn't hide. If you weren't doing well, it was broadcast to everybody. So that kind of motivated you to try and do well. All right. We are going to continue. Last time we were talking about 1.6, and what we were doing, what we finished up last time was we were trying to do limits where our answer was either infinity, negative infinity, or does not exist. There were those three possible outcomes. And I asked you to do a certain number of problems on that homework, but not the whole thing, right? So any questions over those homework problems? It was only it was only a few of them. Yeah, okay, yeah, but stopped at 18, right? So no questions on those?
in 1.5.
You have a question in 1.5? Okay. What was your question? Okay, so I thought I did not assign that one. I did not assign 34. So what was on the schedule was one thing, but in class I modified the assignment. Actually, I sent you an email to say, only do these.
Okay.
Yeah, so be checking those. Yeah, if I have time today, I'll go over that problem because I never showed anything like that in class, which is why I didn't want you to try and do it for homework. Yeah.
That was not happening.
Yeah. Okay. Yes.
I took it, but I don't believe it's in this package.
It's not in there?
Yeah. I looked like it twice and it's not in here.
Pass it around, and then we'll see if there's any leftovers. I'm pretty sure I may have got it. We'll figure it out. Could be sitting on my desk. Do you have a grade online?
Yes.
Do you have a grade online? Did you see?
Yes, I do.
You do have a grade
I
online?
do.
Okay, so I don't know. Okay, anything else? Yes.
Number 40 on 1.5.
Number 40 on 1.5. Oh, okay, yeah, we can do that one. So this is section 1.5, number 40. And it gives you, what is that? Cube root of x equals 1 minus x. And it gives you an interval 0 to 1. So this says here, use the intermediate value theorem to show that there is a root to this equation in the specified interval, which means we just have to show that there is a solution. There's a solution to this equation somewhere between 0 and 1. And it says to use the intermediate value theorem to do that. So it's important to understand that they're not asking you to actually find the solution. They're just trying to get you to show that there is a solution in here somewhere. So the way that we go about this is we move everything to one side of the equation. So in this case, I would subtract 1 on both sides, and I would add x on both sides, and that would give me equals 0. Is that all right? Just can move everything over. And then what I do is I look at the left-hand side of the equation as some function of x. And so what we're really looking for, right, is this can be a tough one. Oh, if that wasn't there, it would have gone.
Yeah.
We want we want to know, thank you, if f of x equals 0 on this interval 0, 1. Okay? That's what we want to know, right? If I call this left side a function f of x, I want to know, hey, is it ever 0 in this interval? So, someone want to help how I'm going to do this? We're just going to substitute in. We're going to check. We're going to see what is the value of that function. What is the value of the function at 0 first? Okay, so let's see what the value of this function is at 0. So if you replace this with 0, cube root of 0, 0, minus 1, right, and then plus 0. So what's that? Negative 1, right? Negative 1. So when we plug in 0, we get negative 1. And what happens when we plug in the other endpoint of the interval? So what happens when we plug in 1? You get 1, right? Because you get cube root of 1, which is 1, minus 1 is 0, plus 1. So you get 1. And that's all I need, because what's happening here is, again, if you think about this visually, if I were to graph the function f, what I've said is at 0, I'm down here at negative 1. Right? So my graph is there. And then at 1, my graph is up here at positive 1. And so to go from a negative value to a positive value, right, this is negative, this is positive, to go from negative to positive, I'm going to have to somewhere in here, I don't know where, somewhere in here I'm going to have to pass through 0, right? Somewhere between here and here. And then also I should state that this function here is continuous, right? It's continuous because it's the sum and difference of a bunch of continuous functions, right? This root function is continuous on 0, 1. Negative 1 is just a constant function, and then x is the diagonal function. So all three of these by themselves are continuous functions. So when you add and subtract them together, this should be continuous, which means that I have to connect these two dots with a curve without picking up my pen or pencil. All right? Yes?
Do you want us to draw the graph?
You don't have to draw it. All,
We just have to state this sentence because it's negative and positive, we know in existence.
That's right. You would say, something like since f is continuous on 0, 1, and goes from a negative to positive, right? It must pass through zero, right? And therefore, you have to have a solution. That's it. You see, it's weird because it's hard to like understand what you're trying to do. That make sense? Okay. Any other questions? Okay, so let's get back to limits. Like I said, we were doing problems where we were getting 3 possible answers, right? Infinity, negative infinity, or does not exist. And then we started to transfer into the second part of 1.6, which is where your answers aren't infinity, negative infinity, and does not exist. The actual limit, the thing that you're going to, that x is going to, is infinite. So let's just pick up with an example here, because it was a long weekend, right? Let's take the limit, let's let x go to infinity, and see if you remember what the strategy is here. How about if we had 4x squared plus 1 over, let's go with 8x squared plus x. So we're going to let x get really, really big, right? Get big, 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 big. And we want to know what happens to this ratio.
We multiply by 1 over x squared.
That's what we'll do, yeah. But we're always going to check first to see what's happening, right?
Yeah.
So if I replace infinity here, or the idea of infinity, a number that's getting really big squared is still really big. Multiply times 4 is still really big. Add 1 is still really big. So the numerator is infinite, yes? Becoming infinite. The bigger x gets, the bigger the numerator gets. And then the denominator, same idea, right? This is getting really big, times 8, plus some really big numbers. This is all getting really big. So we have this infinity over infinity, and whenever we see this, this is bad, right? And so we have to do some algebra. We have to do a trick. So this is just like when we get 0 over 0. But the trick or algebra that we do is different than what we usually do with 0 over 0. Here, what we do is, what was our, yes?
Is it still bad if it's over negative infinity?
Yes, this doesn't matter if it's positive, negative, which, as long as one of these is getting, as long as both of them are getting big without bound, either positive or negative, you still do some algebra or some trick. So what was the technique? What was the trick or kind of the thing I said to do here?
You're multiplying by 1, but you're using the highest exponent. So you're doing like 1 over x squared. If we were x cubed, we do 1 over x cubed.
That's right. You look at the highest power of x in the denominator. And that's what you're going to use to choose this very clever number 1 that you're going to multiply the whole thing by. So I'm going to rewrite this. This is limit x goes to infinity. And I'm unmuted and I am recording. Yes, I believe I am. Okay, so now here comes this special 1. I'm going to multiply by 1 over x squared on top and 1 over x squared on the bottom. And I explained in class last time why we're using this 1 over x squared, right? It has to do with the fact that when we do this, everything in the denominator is going to go to 0 except that highest power. That's going to stay a number. So let's go ahead and just pass it through. We're going to distribute, right? So here, 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 here. So I'm trusting that you are okay with this algebra. Right? What's the first term that I get when I multiply 1 over x squared times 4x squared? 4. Just 4. And then plus, now I do 1 over x squared times 1. 1 over x squared. And all of this over, what, 8? And then plus 1 over x, right? Because when you do 1 over x squared times x, one of the x factors cancels. You're left with 1 over x there. And now we have this very, very nice result that Again, we talked about last class. Both of these are going to go where when we take this limit and let x get huge? What are both of those going to do?
You're gonna get really small.
They're going to get really small. They're going to go to 0, right? They're going to vanish away. That goes to 0 and that goes to 0 when we take the limit. Why? Why? Because your numerator here is what? Fixed, right? And your denominator is getting big. And anytime you have a fixed number over a denominator that gets bigger, that ratio gets smaller. And so now when we do this actual limit, notice I'm not doing limit anymore. We just get the 4 here, and then on the bottom we get the 8, and so your answer is 1/2. Questions there? How about this one? Limit, let's let x go to infinity. Let's go x minus x squared over, oh, you know what, let's go plus, sorry. I'm not ready for that yet. And then let's go on the bottom, the square root of 9x cubed plus 1. Let x go to infinity. Top goes where? Infinity, right? Infinity plus infinity squared, infinity. Bottom goes, well, infinity cubed times 9 plus 1 is still infinite, and then you take a square root. That shouldn't impact it, right? Too much. So we have something that's infinite as well. So this is bad, right? We need some algebra. We need a trick. So I'm still going to do the same thing. I'm still going to look at the highest power of x in the denominator, x cubed, and I need to come through and multiply by something that's going to make this x cubed go away. Just like right here. I wanted this x squared to go away, right? So I multiply by 1 over x squared so that way they canceled. The problem here, and I showed you one of these last class, is that if we're going to multiply by 1, it has to be out here, outside, which means that I can't use 1 over x cubed because 1 over x cubed out here has to eventually get inside this root. So what I'm going to do is this. I'm going to write limit, x goes to infinity, and then let me write this over here. This is our original problem. Left some space out front. So what I'm going to do now, this is my 1, okay? I'm going to multiply by, let's see, I do want the x cubed to cancel, right? So I do want an x cubed on the bottom. But I need to be able to get inside the root. So I'm going to write this, x cubed with the square root. And on the top, I have to do the same thing. Sorry, 1 over. Sorry, 1 over x cubed, my apologies. It's the square root and then 1 over x cubed, the square root and then 1 over x cubed. So let's see why this works. I can put these two roots together now, right? Because we have a property from college algebra that says if you have square root of something times square root of something, you can put them both underneath the same root. So I'm going to go a little slow here. Limit x goes to infinity. Okay, let me worry about the top in a minute. I'm not even going to mess with that right now. That's going to multiply times this. Okay, and then over here, this is going to be a new root. And now I'm going to have the 1 over x cubed times whatever was down there. See that? Those two roots come together, and whatever was underneath each one of them now becomes multiplied underneath. Questions there? Do y'all see that that's going to allow me to get that x cubed to cancel out and leave me with that 9? Y'all see that? Okay. Let's take care of that bottom, okay? Because the bottom piece, I think, is going to work out right now. This is going to become limit x goes to infinity. And then, I think my markers are all starting to die. On the top, how about I write this? 1 over x to the 3 halves. Is that all right with you? That right there. I can take the square root of the top and bottom, can't I? The square root of the top is 1. And then when you take the square root of x cubed, this is the same as taking x cubed and raising it to the half power. But then you just multiply those two powers, so x to the 3 halves. That's just properties of exponents, college algebra. Does that look familiar to you? Square root really means raising to the half. When you take something to a power, you multiply the powers. 3 times a half is 3 halves. So that's why the bottom of that became x to the 3 halves. Now I still have up on top the x plus x squared. Man, these are all bad. And then on the bottom, let's distribute through. I'm going to leave the square root here. Let's distribute through. So what do I get? First multiplication of that 1 over x cubed through here. 9, right? That's going to give me 9. And then plus what? 1 over x cubed. Do y'all see that? I mean, in reality, at this point right now, like this is the only part of it that's kind of like calculus. We have to figure out what to come up with to make something happen. But once we figure this out, it's just algebra, right? Just trying to manipulate things. Okay, what about the distribution through the top? I think this is where students will have some issues. Let me write it out in detail. This is limit, x goes to infinity. When you multiply this times this, you're going to get x over x to the 3 halves, then plus x squared over x to the 3 halves. On the bottom, nothing has changed yet. And now we're going to use that other property of exponents that if you have x to a power over x to a power, you subtract, right? You take 1, subtract 3 halves, and then here you do 2 and subtract 3 halves. So limit, x goes to infinity. All right, when I do 1 take away 3 halves, I get negative 1/2, right? 1 minus 3 halves is negative 1/2.
No, it's 3 halves minus 1, right?
1 minus 3 halves is the same as 2 over 2 minus 3 over 2, which is negative 1 over 2. What do you, this one?
Don't you work the denominator from the numerator? No?
No, I'm using this property here. X to the m over x to the n is x to the m minus n. That's our property.
Okay, had it backwards. Sorry. Gotcha.
That's all right.
Yeah.
Right, so that's the property I'm using right here. 1 take away 3 halves. 1 minus 3 halves, I need a common denominator. 1 can be rewritten as 2 over 2, and then subtract negative 1/2. So that's what this is, right? Sorry, it's x to the negative 1/2, right? Now watch the way I write this. I'm not going to write it as x to the negative 1/2. I'm going to write it as 1 over x to the positive 1/2. You'll see why in a minute. Plus, okay, what's 2 take away 3 halves? 1/2. Right? Okay. 2, rewrite 2 as 4 over 2. And then subtract 3 over 2, you get 1 over 2. So this will be x to the 1/2. Then on the bottom, the square root of 9 plus 1 over x cubed. Are y'all with me or not? All right, now can someone explain why I decided to write this one this way and not as x to the negative 1/2? Because that's going to go to 0, right? We have that property again that, look, now I'm ready to let x go to infinity. If x gets really big, what's 1 over a huge number? This means square root, so the square root of a huge number. Isn't that going to head to 0? It gets smaller and smaller and smaller. So this, I'm just writing what's going to happen. This is going to head to 0, isn't it? Anything else here going to go to 0? When I take the limit, anything else going to 0? 1 over x cubed will also go to 0. Right? Nothing else goes to 0 though, right? What does this go to? Well, that's just 9, right? Nothing, there's no x's here, right? So that's just 9. What about this though? Where's that going to go? Infinity. Isn't it? Infinity. Because this really means, right, the 1/2 really means square root, doesn't it? Isn't that really what that means? And so the square root of a huge number should still be huge, right? So this is going to go to infinity. All right, so let's kind of write this out. When I take the limit, this piece goes to 0. See, no more limit. Plus, this piece goes to infinity over, and then the bottom goes to what? Square root of 9? What's square root of 9? 3. So the top goes to infinity and the bottom goes to 3. What? Wait a minute. What was the original problem? We had infinity over infinity, right? And we did all this work, and now we have infinity over 3. Is this bad? Is this a problem? No, this, not 3. This is infinity. It's infinity. See, look, infinity over infinity is a problem because, well, for the same reason 0 over 0 is a problem. 0 over 0 is a problem because this is undefined, right? Infinity over infinity is a problem because all this is saying to you is, look, the top's getting big and the bottom's getting big, but I don't know who wins. Sometimes the top wins, sometimes the bottom wins, sometimes they compromise. Like the first example I did today, they compromise, right? What was the answer? First problem we did, 1/2, right? So the top was getting big, the bottom was getting big. Who won? No one. They said, let's just go to 1/2, all right? This one, the top was getting big, the bottom was getting big, and there was no compromise, the top won, okay? The top got bigger faster than the bottom, yes? You could analyze just the degree, and you could draw that conclusion. But this is more of an abstract idea in terms of, I'm giving you this, you would have, that argument is only if this is polynomials, right? But what if this was like, I don't know, inverse trig functions that have certain asymptotes and the top would go to infinity? So we want it more of as an abstraction rather than, you know, just specific cases of just polynomials. Does that make sense? I think this is the same thing Andy and I were talking about last class. It's like, yes, in college algebra, you learn these like shortcuts, just look at the degrees and compare. And that's great if you're talking about polynomial over polynomial. Here we want to be more abstract because these aren't always going to be polynomials. Okay? I'll do another example where you don't have that, all right? I'll give you one right now and we won't be able to work it, but at least you'll see what I'm talking about, okay? So like, what about this? What about e to the x over x plus natural log x, right? That's not something that you're going to just be able to look at right away. Maybe you can, I don't know, you can take a guess at it. But e to the x, if you, and we'll talk about e to the x later because it was a college algebra thing, but we'll review it, chapter 3. E to the x looks like this. So if you go to infinity, that function goes to infinity. So the top goes to infinity, right? And then infinity, right, plus natural log function looks like this. And as you go to the right, it also goes to infinity. So you get infinity over infinity here. So who wins? Does this help? I mean, could you guess? Do you think you know who wins? Or do they compromise? You can take a guess. I'll tell you if you're right or wrong. No? See, do you see, though, that this you can't use like, oh, it's just the degree. Just boom, we move on, right? This is more difficult. Now, what happens here is infinity, the e to the x does win, all right? It does win. But I could change this to something like 2 to the x down here. Now it's not necessarily going to be the case, right? So we have to have some abstract way of handling this. All right. Oh, do we understand this? Any questions on this? We actually got an answer of infinity, and that is okay. All right? We just have to be able to deduce from this that our answer is okay. The top gets big, the bottom stays fixed. So just think about a fraction where your denominator stays the same, but your numerator gets bigger and bigger and bigger. That number should get big. Okay? So your answer here is infinity. Ah, I forgot my Klein bottle. Damn it. I had it ready to go. I just left it on the counter. Oh well. Remember I told you I'd try to remember to bring my Klein bottle? When I was in graduate school, my buddy owned a bar. And so I would always be at my buddy's bar on the weekends, you know, and I had a Klein bottle beer mug. I don't think I still have that. I'll have to look for it. But basically, a Klein bottle is an example of a container that doesn't have any volume. So it looks, I'd have to show you one. Maybe I'll find a picture of one. But here, look like a little mug. And you know, on like in chemistry class, they have these like graduated cylinders and stuff where they have these measurements like 0 liters, blah, blah, blah. Well, this one, the Klein mug that I had, said 0 the whole way because it's an example of a container with no volume, right? So my buddy would always fill it up for free because I wasn't really drinking anything because it didn't hold any volume to it, right? Why am I talking about this? All right, let's move on. So let's look at another example, something different. Something that looks a little easier, but actually requires a little bit of thought. So look at that. So let's just talk about what's happening. X is going to infinity, infinity cubed, infinity, right? Minus infinity. So here you get something that looks like this. Infinity, take away infinity. Now, had this been plus, which if you look back at every example I've given you so far, I've made sure it's a plus on purpose because I didn't want to run into this. This is saying you have a number that's getting really big, right? And you're subtracting from it a number that's getting really big. Your answer is not 0 because you don't know how big those numbers are. Does that make sense? It's an idea.